Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So welcome, everyone. It's my pleasure to introduce Miguel Ballesteros, who's visiting. He's normally a professor in Barcelona, but he's currently doing a one-year stint at Carnegie Mellon, where he's been working with a number of really interesting people there and pursuing directions in introducing structure into recurrent neural networks, including like Stack-LSTMs. Has been doing some very influential and effective research in parsing and now beyond. So with that, Miguel, please.
Okay, thank you, Chris, for the introduction. So today I'm going to talk about transition-based natural language processing. You will understand what it is in an hour. So first, you might be wondering, who is Miguel? So basically, I did my PhD in Complutense University of Madrid in Spain. Then during this period, I also started, during a long research stay in Uppsala University, working under the supervision of Joachim Nibre, in which I learned all the wonders about transition-based parsing models. Then I moved to Barcelona, in which I have worked with people in generation and also dependency parsing as well. Then I did also a research stay at Singapore University of Technology and Design, in which I also work in phrase structure, CIF-reduced parsing, and also after that, I moved to Carnegie Mellon University, in which I have worked mainly with Noah Smith and Chris Dyer in parsing and other problems. So this talk is about linguistic structure prediction, in which you basically have sentences like this one, Mark Watney visited Mars, and then you want to infer the linguistic structure. The linguistic structure can be given in many different ways. So one way could be, for instance, name entity recognition, in which you have sentences like Mark Watney visited Mars, and then you extract that Mark Watney, all this chunk, is a person, and also that Mars is a location. So there are other things you can do for linguistic structure prediction, for instance, dependency parsing, in which you get dependency relations between words, and these dependency relations are binary dependency relations, and basically you get like some kind of dependency-based syntactic representation of sentences. So in this talk, I'm talking about a supervised approach to linguistic structure prediction, just in case somebody thinks that I'm doing unsupervised. I'm talking about supervised approach to it, in which I have a tree bank with goal structures. I have basically a pairs with sentence and the goal structure, and the challenge is basically, given a new sentence, we want to infer the structure of this sentence. Okay, so I say that this is a challenge because it is actually a challenge. Mainly, if you want to do parsing of a new sentence, this sentence can be something completely new, for instance, or a sentence that has never been written before, and the parser has to be able to parse this sentence in the proper way, and we expect it to do it like this. So the general approach, or basically the main approach for parsing, is what we call graph-based parsing, or graph-based approach to linguistic structure prediction, not only parsing, because this talk is not only about parsing. So in this idea, you basically build a graph connecting all words. You score all the edges with some kind of machine learning model that says how likely is Diego and place to be attached together, and then we search the highest scoring tree with some kind of graph-based algorithm, and then we produce the dependency tree, or any other basically linguistic structure for this sentence. So the graph-based approaches have some problems. So the problem mainly is the speed and complexity, and the hard inference algorithms that you have to implement in order to do them. But of course, they are also very powerful in the sense that they present a global solution to the problem. And of course, this makes them very attractive for basically people that likes to incorporate all the information they can into their models. The question of this talk is whether we can model linguistic structure prediction problems such as NER or parsing as a sequence of actions, and we can do it at the same level of accuracy as we can do it for graph-based approaches. Okay, so what is a transition-based approach for natural language processing? So basically what we have is a transition system or an abstract state machine. So we process the sentence in a sequential way from left to right. And we basically have normally a buffer that keeps the words that we want to parse or we want to get the structure from. And we may use different data structures. Normally, we use a stack and a buffer, like in CIF-reduce compilers or CIF-reduce parsing, as you may be familiar with. And of course, in each step, we have an algorithm that has to select the best operation, or basically the best class, or the best action to do given the parsing state. And we normally use a classifier, and you can pick the best classifier you want to do this. And basically, people have tried this in many different ways. So they have a lot of promise, these transition-based models, because they are fast and very flexible for different kinds of problems. Basically, they are linear in the length of the sentence because you take an action for each word, and you basically finish whenever you are done with the sentence, and this makes them very attractive. And they are also flexible in the sense because you can come up with any kind of set of actions in order to come up with your problem. Of course, they present other challenges. Mainly, feature engineering is hard because you need to define the features over the stack and the buffer, and you need to do it in a proper way, and you normally need linguistic intuition in order to do that. And also the local optima problem. Since you are making greedy decisions, the parser can come up in some kind of wrong decision at some point, and this can be a problem. So in this talk, I'm basically going to try to convince you that we can actually do feature engineering much better by using a different thing, and also that we can also fix this local optima problem by using a better classifier. So in this talk, I'm going to talk about powerful sequential stack-based approaches for natural language processing, or basically transition-based natural language processing. All of them are based on transition-based approaches with the Stack-LSTMs, which is a cool model we presented in ACL 2015. So I'm going to talk about a transition-based dependency parser. I'm going to talk about how we can do extensions for semantic role leveling, so doing joint syntactic and semantic parsing. I'm going to talk about how we can use also these powerful syntactic models for language modeling and generation. And I'm going to talk about a transition-based NER system that was accepted to Knuckle yesterday. OK, so at the beginning, this is basically how people started doing transition-based approaches to NLP. I'm going to talk about parsing. OK, so what is dependency parsing? So basically, dependency parsing is the syntactic parsing of natural language, in which we have dependency-based syntactic representations of language. Okay? This has a long tradition in descriptive and theoretical linguistics, and is right now very popular. I will say more than increasingly popular. It's very popular in computational linguistics because people, well, we have a lot of tree banks. People have worked a lot on parsing, and we have a lot of baselines to beat in dependency parsing. And of course, the main reason of this is because dependency parsing is very useful for downstream applications such as question answering, or matching translation, or many other purposes in which you need syntax in order to do these systems better. So in a formal fashion, a dependency graph for a sentence, such as this one, is basically a directed graph in which you have the set of nodes that represent the tokens, or basically tokens in basically the words in your sentence. And then you have a set of arcs that are directed arcs that represent the dependencies. So a dependency has a dependent and a head. And these dependencies can be labeled with a dependency type. So basically, you know that one is the subject of visited, and you have it labeled with this subject dependency. So I'm going to talk about the Nibres arc standard, Joachim Nibres arc standard transition system, in which we have three different actions. So you get shift, which, well, in this arc standard parser, you have a buffer and a stack, and then you get three different actions. So the first action is to do a shift, which is to take a word from the buffer and put it in the stack. And then whenever you have a couple of words in the stack, you can create an arc from left to right, or to create an arc from right to left. And this is why you have a couple of actions that are called left arc and right arc. And if you want to parse non-projective trees, such as this one, in which you have basically crossing edges, and there is no way to draw this tree without crossing edges, you can also incorporate a swap action, which we call swap, in order to do reordering. And by using that and a stack, you can do any kind of reordering you want, and you can also parse any non-projective tree for the sentence. And still, even if you include the swap action, the parser is still fast and linear in the length of the sentence. OK, so I'm going to give you an example of how the nearest arc standard transition system works for the sentence that I'm running all over the presentation. So basically, the initialization will be in which you have a buffer full of words, basically the words that we are parsing in this sentence. We have a stack which is empty, and the transition here will be like the initialization. So the first thing to do here, since we have an empty stack, will be to do a shift action, taking the word mark and put it into the stack. And now, whenever we have only one word into the stack, in the arc standard parser, the only thing we can do is, again, to do another shift action. So we will take the word Watney and we will put it into the stack. And whenever we have a couple of words in the stack, we can decide whether to shift another word from the buffer to the stack or to create an arc from Mark to Watney or an arc from Watney to Mark. In this case, I guess the best thing to do is to do basically the left arc between Mark and Watney. And whenever we do this, we basically remove this word from the stack. And now, since we only have one word into the stack, we will create another shift action, and we will have visited into the stack. And again, of course, we can shift Mars, or we can create an arc between these two words. So the parser or the classifier decides that the best thing to do is to create this arc between these two words, and then it keeps going, shifting the word Mars into the stack, and finally, it will create the arc between visited to Mars. So this is how a transition-based dependency parser works. And you can see you have all the actions here, and the number of operations is actually linear in the length of the sentence because you have 8 actions and 4 words. It's always twice in the arc standard parser. So the question is, given a parsing state, the classifier has to select the best action. So how do we do that? Well, we need features. And these features are basically things that we define over the stack and the buffer. So during my PhD, I did this system maloptimizer, so I know very well about how to do feature engineering for transition-based parsers. So basically, people define features over the stack and the buffer over a fixed window of features. Like saying, OK, I take the first couple of words of the stack, the first couple of words of the buffer, and I define like singleton features over a part of a speech, word forms, etc., etc. And by using that, I can fit everything, all these features into a classifier, and the classifier will make predictions. So this is how a feature set looks like normally, like the standard feature set or the default feature set looks like for a transition-based parser. These are like merge features, a couple of things. And as you can see, you only go, input will be the buffer. You only go to length 3 or something like this. But now we can do it better because we have recurrent neural networks. And we can have like basically, we can have a better look ahead of what is coming out of the buffer and what we have in the stack. So we can use recurrent neural networks to do transition-based parsing. So the idea is that recurrent neural networks are good to learn to extract complex patterns from sequences. They are very good for data which is order and context sensitive, where the later elements of the sequence depend on previous one. And it basically means that we have like what we have in transition-based parsing, which we have a stack and a buffer. And these basically they are order and context sensitive. They are also good remembering information over long distances. But recurrent neural networks, as they are with the simple implementation, they have a bias toward representing the most recent information. And this is what people call the vanishing gradient problem. So some people came up with the idea of doing LSTMs, or long-term memory networks, which is basically a variant of these recurrent neural networks, which are designed to cope with these vanishing gradient problems. So they basically have an extra memory cell that keeps gradients and decides when to keep the gradient and where to not keep the gradient. And by doing that, you improve the results of RNNs in many tasks. So they are better than RNNs in several tasks, and also in parsing. And what we presented in ACL is basically, so we have an LSTM, as you know, is a sequential modal encoding of a sequence. So in transition-based parsing, we need stacks. So we basically change LSTMs with a stack pointer and 2 constant time operations. So basically, the constant time operation, the push operation that we have, will be the same as we have in LSTM whenever we have an input. We add a new input into LSTMs. And then we also have a pop operation, which basically moves the stack pointer back And by doing that, we can basically model the behavior of a stack. And we can do parsing in a very efficient way by using Stack-LSTMs or LSTMs. So the intuition behind these Stack-LSTMs is that the summary of the stack contents is basically obtained by accessing the output of this stack pointer at the location of the stack pointer. So I'm going to give you an example of how this works. So this will be our, well, I'm going to be here. So this will be the Stack-LSTM, okay, in which we have the stack pointer pointing to the output of, so this will be like the output layer, the header layer, and the input layer of the Stack-LSTM. So it will be for this stack in which we only have one word mark. The output is pointing to the output layer of this one, okay? So now if we do a pop, basically we remove the symbol from the stack. What happens with the Stack-LSTM is that the output layer, the pointer is basically pointing now to the empty stack. So as you can see, we can model any kind of a stack. And if we make another input, basically shifting one into the stack, now the output layer, the pointer is basically this one, which is what we need. If this is difficult to understand, I have another slide, which is the next one, which I think is going to be better for some people. Some people like this one, some people like the other one, so I decided to keep both. So basically, if you are doing push, you are doing the same thing as you do in an LSTM. And whenever you do pop, you basically move the pointer back to this. And now if we do push, we basically create like another branch in a tree for doing like this. Yeah?
So there's only one stack total?
At the end, you have one stack, yes.
But it's complex, it's got a structure to it.
Yes. So at the end, for instance, if you are here and you want the output of your LSTM, you just run the recurrent neural net for whenever you get the pointer.
So you don't need to remember those other branches, right?
You don't, but if you start removing them, the complexity grows, and you don't want that. So the idea here is that we just need to keep whatever we need for this. And of course, all these things, you can get rid of them but for parsing. Yeah, any more questions here?
So this is the same kind of model that appear in NIPS.
What NIPS? NIPS are not of models.
So this is earlier than that one. I saw the same paper, or maybe different author. Is it a different kind of model or the same?
Well, this is a Stack-LSTM which was published by me and other co-authors in ACL 2015.
We have a continuous presentation stack. So this one seems more discrete.
Okay, shall I keep going? Any more questions about this? No? Okay, so this is basically what we use. So these are the Stack-LSTMs in which whenever you want to you get like the encoding of a stack, you can do that. So we are augmenting LSTMs with this stack pointer, and this allows us to basically build stacks and do parsing, what we need in transition-based parsing are basically stacks. So the next question, of course, is how we can use this to do transition-based dependency parsing with Stack-LSTMs. So we have a buffer, as you know, because I showed you the sample. We have a stack, and we also have a list with the history of actions, which are basically the things that the parser has done so far. So this list of actions, this buffer, and this stack are basically associated with a Stack-LSTM. So we have an encoding of the components of the stack, the buffer, and the list of actions at any time step. The list of action is not a Stack-LSTM because you are only pushing things into this. You are never popping things from the list of actions because you cannot change the past. But the buffer and the stack are basically Stack-LSTMs. And we use a rectifier linear unit to produce the parser state embedding given the three Stack-LSTMs. So this thing basically looks like this. So this will be like the buffer in which we have the stack pointer pointing to this element here. We have also the Stack-LSTM here for the stack. And we have the Stack-LSTM for the list of actions with the actions taken so far by the parser. And this, of course, is the rectifier linear unit and the softmax over the actions, and the parser decides what to do given the encoding of the three Stack-LSTMs. So since this is a neural network parser, we have to represent the words in the best way possible. So we have word embeddings, okay? So as you can see here in the previous slide, a lot of the things here, basically, they are words. So we need to represent them So basically, we have a learned vector representations for each word type. So these are these vector representations that you see here. So these are taken from the training corpus, and we get a learned vector representation, a learned representation for them. And for each out of vocabulary words, we get a fixed representation, like ANC for the words that are not included in the training corpus, basically OOV words. We also have pre-trained word embeddings by using a neural language model pre-trained word embeddings by Lin et al. in NACL last year. And these are basically another word embedding that you can have here. And we also have a learned representation of the part of the speech stack. So what we do is to concatenate these 3 different vectors, and for each word, we get a new embedding as this. And another thing which is very, very useful in transition-based parsers is the composition functions. In transition-based parsers, we normally call these history-based features, which are the things that have already been decided. So imagine that you have already found the subject for a sentence, so you don't want to find another subject for the same verb, right? So you get composition functions are basically the embedding of a subtree, of a dependency subtree. So as you see here, you have over-Hastian decision, this is a subtree, and we want to get the best embedding possible from it. So what we do is basically to run a recursive neural network or hyperbolic tangent or the head, dependent, and relation plus some kind of bias. So you have the word over-hasty and decision, you run this hyperbolic tangent of over-hasty decision with the relation, and then you get an embedding from it. And this is basically how we represent partially with dependency structures, which is a very, very useful source of information in parsing.
So
yes?
Quick question. There's in the case where you only have dependence on one side, it seems like it's unambiguous about how to compute this tree. But if you have dependence on both sides, there's ambiguity about whether you pull in the left
yes,
or right.
there is ambiguity, but you're always starting with head dependent and then relation. So you.
But there could be, say I have, let's see, English is tough, but well, even if I just say John went home.
Mm-hmm.
Went has 2 children. One is John and one
yes.
is home. And does it matter in the order in which you consume the children?
It does here. It doesn't matter. So you will get like a different embedding in which one will be a left and the other one, but
you just pick it.
You just pick it whenever the parser. But since it's a left to right parser, you normally get the same order at the same time, unless you are doing swapping and non-projective parsing, which it can change. Yes.
Why for English? Why is it a left to right parser?
Is because we are using a transition-based approach for parsing, in which we basically shift words one by one from the buffer to the stack. So it's always a left to right parser.
But could it not have equally been a stack but going from right to left?
You can. We tried actually to do it in the other way, and it works similarly. Yeah.
I'm just thinking because English by default has right branching structure.
Yeah.
So it's actually maybe easier to go from right to left.
So some people have tried several ways, like doing first left to right, then right to left, and try to some kind of voting system between these two, and they get a little bit improvements, but it's not like the most influential application you can imagine. But of course, you since this is a transition-based parser, you have to think about always left to right parsing, in which you can also swap words if you want to have non-projective parsing in German or Czech or these languages. Yes.
But at any point in time, you have information from left to right.
Yes.
How about doing something bidirectional?
Yeah, but this is what we are talking. You can do it bidirectional. But in this case, we are only what to think about is like a transition-based approach in which you take words in a left to right fashion. Okay. Sure. Okay, so these are the experiments that we ran first. These were the ones that we ran for the ACL paper. So these are for the English pen tree bank. So we have the Stanford dependencies. We use the predicted part of a speech task with the Stanford tagger with 97.3, which is state-of-the-art accuracy for this tree bank. And then we use basically the same settings as Dan Kitchen and Chris Manning, which is a feed-forward transition-based parser, also left-to-right neural network parser, for which is the closest model published to our Stack-LSTM parser. So we compare our results to the results. So we see that, well, basically this is a label attachment score is the percentage of scoring tokens with a correct head. And label attachment score is the percentage of scoring tokens with a correct head. And we also take into account the label. Okay? So as you can see, the results compared to Chen and Manning, we get more than 1 point here. And for label, we more or less the same result, like 1 point better. So our parser is basically better in all conditions compared to Chen and Manning. What I'm going to show you now is like an ablation conditions in which we remove the components that I presented before, so the composition functions, the word embeddings, or the part of speech tags, and see how the parser reacts to that. So if we remove the part of speech tags, the parser goes down to 92.57, like what attachment score. People normally take into account this column in order to compare parsers. So 92.57, actually 92.6 is like the best, one of the best results published without part of speech tags. So this is a very, very strong result. If you remove the pre-trained word embeddings, you see that the parser gets like 92.4. So you are removing all the semantic information or all the contextual information that you have in the word embeddings. And you see that the parser suffers, but it still is very competitive. And if you remove the composition functions, or basically the partially built dependency structures, and when I say remove it, basically what we keep in the stack is the head, instead of keeping the embedding of the partially built tree, we keep only the embedding of the head. And if you do that, the parser goes to 92.1, which is, of course, it goes in line with previous research in transition-based parsing and history-based features. Yes?
Is this cumulative or is this each?
No, it's not a cumulative. It's this one.
So you put the part of speech tagging back in before.
Yes. This is why they are in the same level. But that's true that it's a little bit confusing. Okay, and if we remove the Stack-LSTM, we use a stack RNM. So instead of using LSTMs, we use RNNs. The parser gets 92.3, which is still better than Chen and Manning, which is a feed-forward neural network, but of course it's not competitive compared to the Stack-LSTMs. And then we did experiments with the Chinese tree band. So for this Chinese tree band, we follow basically Yue Yan and Stephen Clark, which are the people that started doing experiments with this tree band. We use gold part of speech tags, and this is basically, again, the same settings as Danki Chen and Chris Manning for this paper in EMLP. So here we have more or less the same picture. So the Stack-LSTMs are, well, here are better, like 3 points better than the Chen and Manning parser. These are state-of-the-art results for these settings. And again, if you go for the ablated conditions, you see that there are differences. If you take into account the part of speech tags, you see a big drop, and this is because we are using gold part of speech tags in this case. And so here is like the improvement of part of speech tags is higher. Okay, and well, basically some conclusions of this part. So this is the highest result ever published for a greedy parser, for a greedy left-to-right transition-based dependency parser. Is very close to being search or complex graph-based parser, or even I would say is better than most of them. So this is actually something very, very influential, and it runs in linear time with greedy decisions. So you get decisions, you get a parser which is super fast, and it provides one of the best results ever published. Okay, so any questions so far? Because I'm moving to a
I had a
different
question about several slides ago, you were supplying the part of speech tags as an embedding. But I mean, there's only 40 part of speech tags. I don't understand what an embedding of.
Well, it's a small embedding of 12 dimensions. But yeah, it's basically a random embedding that we learn during training. In some languages, you have more than 40. See, you go to Korean. I'm going to show examples or results in Korean later. You have a part of a speech tag that is basically like 1,000 different parts. It's not like the language in which you have 22,000 or something, but it's 1,000. So you can have something there. Okay, so let's move to the character-based modeling of words. So as you remember, well, actually going from the question, we have like an embedding of part of the speech tags, and then we also have like a pre-trained word embedding and a learned representation of the words from the training corpus. So we can do something better. We can do character-based modeling of words. So imagine that you can also run a bidirectional LSTM character by character of the words of your input sentence, and then you run it in the other direction, and basically you concatenate these two embeddings together, and you concatenate this with the embedding of the part of the speech tag. So the intuition behind this is that you are going to get a lot of suffixes and prefixes from the character-based embedding, And also that you can do this for every word. You don't need to care about whether this was an out-of-vocabulary word or an in-vocabulary word. You can actually do it for every word in your input sentence. This was published in MLP 2015. I'm going to show you the results later. So basically, we model this character-based modeling of words in a two-dimensional thing. So we basically took the embeddings and we ran it with TSNE and we got this. And as you can see here, we see a cluster of words that are basically words in past tense for English. You also see a lot of gerunds here. You see some adverbs over here. And you see the same word endings of these two words here. Or you see the same word endings of these two words here. So you see a lot of basically suffixes and prefixes. And this information is something which can be very useful in parsing, because suffixes and prefixes is what gives you the morphology and part of the speech study. So by doing these character-based embeddings, the intuition and the motivation is that we can improve out-of-vocabulary handling, and we can improve the performance for morphologically rich languages. So we did this experiment in which we have this baseline model, which is what we call words. I put this here because it's in the tables. And we also have this character-based model, which we call chars. So this baseline model is the same one as I presented results in Chinese and English before, but removing the pre-trained word embeddings. So we don't have additional resources. We just have the pre-trained word embeddings of the tree bank. Okay? So we did experiments for some tree banks of the CERTAS on parsing morphologically rich languages. These are basically Arabic, Basque, French, German, Hebrew, Hungarian, Korean, Polish, and Swedish. As you can see, some of them are agglutinative languages, and you basically agglutinate morphemes. And we also included Turkish, because you know that Turkish morphology have this agglutination behavior, which is going to be very impressive with character-based modeling. And in terms of completion, we also run it with English and Chinese. So we don't have any explicit morphological features, just to see the effect of character-based representations. And we don't have additional resources, just the training corpus, the parser, and no pre-trained or character-based embeddings. So we tried with and without part of speech as well to see the effect of character-based modeling of words. Okay, so if we try with analytic languages such as English or Chinese, you see that the parser with character-based embeddings is better, like 1 point, well, for English it's only 0.3 or almost 1 point for Chinese. But of course, we didn't expect too much for English or Chinese, because these are analytic languages in which morphology is not playing a big role for syntax. But if we move to agglutinative languages such as Basque, Hungarian, Korean, or Turkish, you see very big improvements. So you see how the parser for Basque have more than 6 points improvements. For Hungarian, it got like 8. For Korean, it got like exactly 10 points actually, and for Turkish, it got more than 3 points. So you see how the parser actually behaves much better when using character-based modeling of words, comparing to how it behaved having the word representation like the sequential thing. And if we tried with fusional or templatic languages, we see how the parser also improves in all of them. So as you can see, this column is all over it in bold. And as you can see how we also improve in all languages. In Polish, we saw a very, very big improvement. And the main reason why we saw this improvement in Polish is because the out-of-vocabulary rate in this tree one is super high. So we basically are seeing that the character-based modeling of words are giving you something a lot, also when you have out-of-vocabulary, higher out-of-vocabulary rates. In some languages, you see more or less the same result, such as Arabic or other languages. And when we include, this is without part of speech tags, all these experiments, okay? And when we include part of speech tags, we see that the pictures change a little bit. So for English and Chinese, you almost get the same numbers, or a little bit better for words. But you see that the bold things are always in the agglutinative languages. So it's still Turkish, Hungarian, Basque, and Korean, which are agglutinative languages. Basically, when you agglutinate morphemes and you get these kind of things, you basically see that you still get very big improvement. For parsing, more than 2 points is a lot. And in average, the parser is better compared to the one with word representations, as you can see here. Okay, so the conclusions for this is, of course, character-based representations are useful. they obviate part of speech information for some languages. So actually, if you compare this column to this column, in some cases, you go to Korean, for instance, it's actually even better when you don't have part of speech information. So you are getting better information from the character-based modeling than what you get with part of speech tags. And they are more useful for agglutinative languages. In our examples, these 4 languages are in which you can see actually a very big improvement. And it's also a nice approach for handling the out-of-vocabulary problem we saw in Polish, in which, well, when you have a big out-of-vocabulary rate, the parser gets better. So we have an article submitted to computational linguistics, still waiting for the reviews, but somewhere it will. So with all the results that I have presented before. Okay, so well, in this fall I had the chance to basically teach a course in natural language processing. So one of the things that I taught is about the parsing. So I asked the students to build a parser. So I had this student who is working with me, and we built this ensembling system by using different outputs of different models produced with the Stack-LSTM parser. So basically, you train several models with the Stack-LSTM parser, and you build a voting system like this one, okay, in which like 40 parsers things that the one place will be attached together. And then you run a graph-based parser, a Julian-most parser, and the result that we got is basically the best result ever reported for dependency parsing, and we are working a research paper together for this. And also, we can do this cross-lingually. So Walid was interested in this parser, and we were working basically in this cross-lingual setup in which we train a language universal dependency parser on a multilingual collection of tree banks. So basically, instead of training with a monolingual tree bank, we train it with several tree banks. And we also have multilingual word embeddings and typological information included into the parser. And the nice result about this research was that the multilingual training outperforms standard supervised training, which we have a monolingual training. So this result is submitted to tackle. We will expect the review soon. And basically, this is the main table. This is the monolingual training, in which you basically take a tree bank for German and you train a model for German and you get a result. The result for English is only 88 because this is the universal dependencies. You only have 12,000 words. You don't have the size of the pen tree bank. And the nice result is here, basically. So you compare this to this, and you see that the multilingual training is better than the monolingual training. Basically, all the columns is the language universal, in which we train with all languages and you evaluate on German. And here is when you include lexical embeddings for the target language, language ID, typological information, and fine-grained part of speech tags, and you see how the parser is better. The implications of this are very high, because if you want to parse difficult languages in which you don't have any data, well, you can use this model, and it's expected to be better, actually, than the monolingual training. And we compare this with the state-of-the-art, with the same systems. So this is when you don't have any data of the target language, and we are better than state-of-the-art systems in this sense.
I'm sorry.
Yes.
You're saying you don't have any data, so then...
So you basically, this is Swedish. Okay. So you remove all the sentences from your training corpus that are in Swedish, okay, and you train with all the other languages, and you evaluate in your Swedish test set.
So when you say plus lexical, what does that mean?
It means that you use explicit embeddings for the target language that are trained with for this language.
So trained on some monolingual data?
Yes, in monolingual data. Unlabeled data, which you could take for any language, for most of the languages.
Sorry, can you go back one slide?
So, of course.
When you supply the language ID, what is that?
The language ID is the typological information, so linguists will tell you probably better than me, but basically it gives you like how the parse, so how the syntactic information is behaving in each language. So you know how the left branching or right branching of the language.
But in what form is it fed to the model?
Sorry?
How do you give that?
It's basically like a signal for so you remember the 3 Stack-LSTMs?
Right.
So you get like a signal, another embedding for the language ID.
Okay.
So you have a set of typological features. Is it
Yes.
SOV or SVO or so on and so forth?
Yes,
Is it agglutinative
Exactly.
or fusional? And so you have these k different features and a
And
one-hot
you
representation.
you input an embedding of this to the parser, and the parser makes better prediction, as you can see. It improves for all languages, actually. In some languages, you actually see a big improvement. So if you go to German and you include the topological information, you see that left attachments improve a lot, which is something that I found interesting. That the parser, when it didn't have this typological information, was trying to do a lot of right attachments. We include this, and the parser started to do it better. So, well, I think it's a nice result. Okay, so now this is basically all the parsing stuff. So as I promised at the beginning, I'm going to talk about something different to parsing. So the question is if we can model other linguistic structure prediction problems different than parsing as sequences of actions. So hopefully I convince you that we can do it for parsing. And we can try to do it for other problems. So the question is whether we can model them jointly with syntactic parsing. So having syntactic parsing joined with another task, or we can model a particular problem with their own set of actions. I'm going to give you an example of these two questions. So first, talking about joint syntactic and semantic parsing with Stack-LSTMs. I'm going to briefly explain about this. It's another paper submitted to tackle. So we have a joint model for syntax and semantic role labeling, basically using Stack-LSTMs. So instead of having one stack, we have a couple of stacks. One that keeps the syntactic information and another one that keeps the semantic information. So in one of them, we keep all the partially built dependency structures that we get from the syntactic stack. And the other one, we get all the semantic roles that we can get from the stack. And we got state-of-the-art parsing and semantic role labeling from this by using, again, the Stack-LSTMs. So we compare with previous systems. These are the system of the Cornell 2009, Cornell 2008. And this is the closest model published, which is James Henderson's model, which uses actually the same algorithm, but without using Stack-LSTM, by using neural networks, actually. So we see how we improve his result, especially in the semantic task. Okay, and now I'm going to talk about one paper that got accepted yesterday in NACL 2016. So this is basically it's a paper called Neural Network Models for Native Recognition. And one of the things in this system is a transition-based NER model with the Stack-LSTM. These are the two main collaborators of the paper. So basically we have an algorithm that constructs labels chunks of input sentences. It's a transition-based approach again. It is the same way as we do it with the dependency parser. In this case, we have three data structures. I'm going to give you an example of how this works. We have a buffer, we also have a stack, and we also have an output buffer that keeps the things that have already been decided. And it's a similar approach to the parser. So let me give you an example of how this works with the same running example. Our friend Mark Warney, which is tired of being in Mars. So basically, you have a buffer full of words, you have the stack, which is empty, and you have your output buffer, which is also empty at the beginning. So the system basically decides to make a shift. It takes a word from the buffer and put it into the stack. Now it can decide to say, well, Mark can be already an entity, and it can go to the output buffer, or it can create a chunk with another thing, so shifting another thing into the stack. And whenever we have this, again, you can decide to create a chunk between these two words or shifting another thing. In this case, it decides to basically reduce, what we call reduce. And it's basically taking Mark Watney and creating this. And basically, I'm going to explain you how to put this information in an embedding here in a nice way to improve the results. Of course, when you have a verb like visited, it's not an entity, so we can basically get rid of it. And what we do is to put it out to have an output transition that basically takes visited and directly throws it to the output buffer. And of course, you can also shift Mars into the stack. And whenever you have this, since there is nothing else, you can decide what is the best entity to have for this thing. And in this case, it's location. So this will give you like the result for this sentence for NER. Okay, so the main motivation of this research is that most NER systems use external resources, as you know, as people that have worked with probably know. So they look into gadgetiers, external databases, resources. We can do that, of course. We can input that into our model, but we don't want to because we want to do this also for a low resources scenario. So the question is if we can perform at the same level or even better without including any of these external resources such as gadgeteers or external databases with information about entities in the world. So we did experiments with the Connell 2002 and 2003 datasets for English, German, Dutch, and Spanish, and we only use word form features. We didn't even use part of speech tags to make this like cross-lingual and multilingual, or in which you can actually try with everything like this. So this is how the system looks like. As you can see, it's similar to the parser. You have the Stack-LSTM for the buffer, you have the Stack-LSTM for the list of actions, you have your Stack-LSTM for the output buffer, and you also have a Stack-LSTM for the stack. And then you get the softmax of the previous actions, and you basically decide what to do given the parsing state or the system state in this case. So in order to come up with a nice way of representing words, what we did here is to do character-based modeling of words again. So because we thought, okay, character-based model is going to be very useful also for NER because you have also the capital letters at the beginning. All these things are very, very useful. And we also have pre-trained word embeddings with a lookup table with basically the same embeddings that we used for the previous publication in parsing. We use it here in a lookup table. So basically, for each word, we run a bidirectional LSTM. For the word Mars, for instance, we get like this. And then we have a lookup table for the embedding of Mars, and we concatenate these two vectors together. And this is our embedding for the system. And again, we have also composition functions. So whenever we reduce, whenever we take a chunk from the stack and put it into the output buffer, we have to infer some kind of information and put it in some kind of embedding. So what we did is basically to run a bidirectional LSTM over the embeddings of these tokens together. So imagine Mark Watney, we run a bidirectional LSTM over these two tokens together. And we also include the label, so in this case, like location or person or whatever. And then we get a representation, which is what we call composition functions of bidirectional LSTMs. Okay, so these are the NER English results. So this is the result of the Stack-LSTM parser. This is another system that we presented in the same paper, which is actually a little bit better, but it's the same level. So all the systems with a star are systems that incorporates basically external resources or part of speech tags or gadgeteers, linking, etc., etc. And our system only uses word forms, nothing else. And as you can see, the results are actually very, very competitive. This is one of the best results actually published for NER. The same picture is for other languages. So if you go to Spanish, you see how the system, the Stack-LSTM system gets like almost 84. Is the best result ever published, and the LSTM CRF system, which is a bidirectional LSTM thing that we have in the same paper, is also a little bit better. And for Dutch, you also have the same picture. So this system uses a lot of external resources, and you compare with the rest. We have like the best NER system by only using word forms. And for German, we have the same picture. Of course, we see that the character-based embeddings, as we saw in parsing, are extremely useful. So you see that they have a big impact into the results of especially the Stack-LSTM model. So, well, this is the state-of-the-art NER system. It's linear in the length of the sentence, so again, it is fast, as we have with the parser. So basically, we can run it in a very fast way, and we can produce very, very nice results. Again, character-based representation happen with the dependency parser. They provide very, very useful information for NER, such as you can have like auto-vocabulary words or other things. And we are only using word form features, so we are not even including part of speech tags in the model. Of course, we could have included, but this was not the, and when we included it, we improved, but this was not the task of the system. And we don't have, again, no gadgeteers, no external resources. So now I'm going to briefly talk about another paper that was accepted to NACL 2016. So basically it's what we call recurrent neural network grammars. So this is a top-down phrase structure parser. So it's not dependency parser, it's phrase structure parser. And we also include language modeling results, and we again use Stack-LSTMs. So the nice thing is that this Stack-LSTMs for syntactic parsing that I showed you before is a very powerful discriminative model for language, basically. So you can basically infer syntax in a very nice way. But syntax, as you know, is very useful for generative language, okay? So the idea here is that we can use the same things that we have in the Stack-LSTM parser to basically create a generative model that can be evaluated as a language model. So think about it. Whenever we shift a word from the stack to the buffer, we can also predict what word is. We can decide what word is depending on that, so we can actually use it as a language model. So we do this in the context of phrase structure parsing, and we call it RNNG, so basically recurrent neural network grammars. So this works more or less like this. It's a top-down parser. It's not like a typical phrase structure parser that basically is bottom-up. So you have the buffer here. This will be like the discriminative version of it. You have the buffer, and then you can also shift terminals into your stack. At the end, you are basically building the phrase structure tree of your sentence. The nice thing is whenever you shift, you can also predict the word, and then you can evaluate it as a language model. And the language perplexity result that we got for the English pen tree bank, so if this is a sequential LSTM, basically an LSTM in which you predict the next word given the encoding of the previous elements, we get better results including this syntactic information of the Stack-LSTMs for both English and Chinese. So you can see we have an improvement here and here. And the nice thing is that we can also evaluate this as a parser because it's a parser. And if you go to the F1 scores for the English pen tree bank, you got without external resources 92.4, which is state of the art. One of the best results ever published for this parser, for this tree bank, sorry. And for Chinese, it's close to the best, a little bit worse. The best one is around 83.2 or something like this. But it still is a very, very competitive result, taking into account that game is greedy, left to right, and you don't need any external resources. And this is something that we are starting, the more ongoing work. So we are thinking about this transition-based approach to matching translation, in which, well, as at the beginning I said, with a stack-based parser and a swap operation, you can actually come up with any kind of reordering. So if you have a buffer, yes, you can.
You can do ITG reorderings.
You can do any reordering.
We'll have to talk about that at some point.
Okay. I can show you.
Yeah.
So basically, you have well, it's hard because the number of actions it can grow, but you can come up with most of the reorderings. If you go to some languages such as Japanese, English, it's going to be more difficult.
It's a restriction that, yeah, but anyway.
Well,
this is a total minor detail. Please go on.
Sure, no problem. Anyway, so basically we are starting on this, we are starting thinking about this. So looking at the results of our RNNG grammars, in which language modeling results are super nice. And we can also do transition-based parsing and non-projective parsing, in which we swap words and we do reordering. What about instead of shifting a word from the source language, we shift a word from the target language. So we make a prediction of the target language. So basically we are thinking about this and basically supervising this student on this. And basically the final goal is to do a complete matching translation system that runs in linear time. This is a very big project, a very big goal, but we are trying to do it and I believe it's possible. So it might be also interesting to do it jointly with parsing. So whenever we shift a word, we also produce the syntactic parsing. So using these embeddings can be useful for matching translation because as you know, syntax is also useful for translation. So this is something we are trying to do right now. So in conclusion, yes, sorry.
Sorry, you were saying about linear time. I mean, doesn't the Montreal LSTM model also run in linear time? I mean, it's got a very large constant, but
yes,
it's also linear, right?
Yes. It is, definitely. But in this case, the idea will be to do everything in one single step, even reordering. So.
Yeah, but I mean, that's sort of what the Montreal attention models do as well, right?
Okay, so in conclusions for this talk, so I presented powerful sequential models for natural language processing. Basically, all of them are based on transition-based approaches with Cyclist. So I presented state-of-the-art transition-based parser, which is getting a lot of attention from the community. It's good in both in terms of results and speed, because, well, it runs in linear time, greedy decoder, and it produces one of the best results ever published. I also presented a fresh and new state-of-the-art transition-based NER system that produces very high results without using external resources that can be extended to many languages and many tasks by using the character-based embeddings of words. I presented how we can do extensions for language modeling by using a shift-reduce approach, in which whenever you shift a word, you can also predict the word from the buffer and use this as a language model. And I saw that we can produce state-of-the-art results also for language modeling compared with a powerful LSTM. And also, briefly, I presented extensions for semantic role leveling, in which you can do joint syntax and semantic role leveling with Stack-LSTMs. Sorry. So I would like to acknowledge Noah Smith and Chris Dyer, which are advisors on most of these papers and collaborators in my case of all these papers. And I would like to thank you, all of you, for your attention. And if you have any questions, I will have to answer. Okay. No more questions? Yes.
There was one of these mini papers where you had an output, input, and a stack.
Yes.
It sounded like you used Stack-LSTM for each of them as opposed to just on the stack one. I was just curious.
So basically, the parser you mean? So
yes.
For instance, this?
Yes.
So each of them is a Stack-LSTM, yes. So basically, in the case of NER, basically at the beginning you do always push for the buffer, for instance, you always push all the words, and then you start popping things. Whenever you shift something from the buffer to the stack, you start, so it's a stack.
Yeah.
But in the case of transition-based parsing, so if you go, let me go back. So in the case of transition-based parsing, so this is the same. So we fill this with all the words at the beginning, and then we basically shift things. Whenever we shift, we pop. But if you do non-projective parsing with the swap operation, you basically take this word and you put it back here. So you also do pushes during parsing time. So it's stuck totally. But this list of actions can be modeled with LSTM because it's basically history, and you are always pushing things. You never pop for it. But yes, all of them are Stack-LSTMs.
Great, thank you.
Okay.
Thanks, everyone.
Thank you.